Imagine a fighter jet that's not only an extension of the pilot, but also a semi-autonomous partner, capable of analyzing complex battle scenarios in real time. That's the promise of the U.S. Air Force 6th generation fighter jets, or at least it was. At the end of July 2024, Secretary Frank Kendall announced that the Air Force's next-generation air dominance program would be paused for a few months to see whether it is on the right course. This review stems from the need to align the jet's design with evolving threats and budgetary constraints. If confirmed, these aircraft, crafted for stealth, speed, and agility, are poised to redefine the strategic landscape of air warfare. But what makes a fighter jet 6th generation, and how do these marvels of technology stand out from their predecessors? While 5th generation jets like the F-35 focused on stealth and sensor fusion, 6th generation jets are expected to push these capabilities further. They will feature enhanced stealth, making detection even more difficult, and utilize adaptive engines for superior efficiency and performance. Moreover, with advanced artificial intelligence on board, these jets will be capable of making split-second decisions, with the potential to operate autonomously or unmanned. The NGAD program, initiated by the U.S. Air Force in 2020, evolved from DARPA's 2014 Air Dominance Initiative, which emphasized the need for a comprehensive suite of technologies to achieve future air superiority. The primary motivation behind this ambitious project was to develop a family of connected air warfare systems that can dominate the skies in future conflicts. This includes everything from manned fighters to drones and other supporting airborne assets. The primary motivation behind this ambitious project is to not only replace aging jets like the F-22 Raptor, but to revolutionize air combat. NGAD is envisioned as an adaptive, versatile system that can dynamically respond to evolving threats and seamlessly integrate with new technologies as they emerge. Let's have a look at the broad range of proposed specifications for a 6th-generation fighter craft. At the core of NGAD's cutting-edge technology is the development of adaptive cycle engines, which promise to revolutionize the way fighter jets perform in various flight conditions. These engines stand out for their ability to switch modes mid-flight, offering optimal performance whether the jet is cruising long distances or engaging in high-intensity combat scenarios. Traditionally, jet engines had to compromise between fuel efficiency, necessary for long-range missions, and the sheer power required for rapid acceleration or dogfighting. This balance often led to sacrifices in either speed, maneuverability, or fuel efficiency. However, adaptive cycle engines eliminate much of that compromise. By leveraging variable cycle technology, these engines can dynamically adjust how air flows through the engine. In high-thrust situations, such as during a quick ascent or in combat, the engine directs more air into the core to maximize power. Conversely, when cruising over long distances, the engine increases its bypass ratio, allowing more air to bypass the core, which greatly improves fuel efficiency. The key benefit? These engines allow NGAD fighters to sprint to supersonic speeds when necessary, and then seamlessly transition into a fuel-efficient mode without relying on external fuel tanks, which could compromise stealth. By keeping external fuel pods off the aircraft, the engine supports both long-range operational capability and enhanced stealth characteristics, critical to maintaining the jet's low radar profile. In addition, adaptive cycle engines are designed with multiple fans and variable air intake methods, which enable the engine to adjust its performance to match the aircraft's current needs. Whether the fighter is taking off, cruising at high altitudes, or engaged in combat, the engine can recalibrate to provide the best balance of speed, power, and efficiency. The next-generation Adaptive Propulsion NGAP program is developing the propulsion systems that will power NGAD, with prototypes from both General Electric, XA-102, and Pratt & Whitney, XA-103, currently being developed and tested. However, the program has faced some challenges, particularly regarding the complexity and cost of these engines. Air Force Secretary Frank Kendall has suggested exploring simpler, potentially smaller alternatives to manage these issues, though the adaptive engine technology remains a critical aspect of ensuring long-term air dominance. Shifting focus to stealth, the NGAD program integrates advanced technologies that minimize the aircraft's detectability across multiple spectrums: radar, infrared, and acoustic, reflecting the U.S. Air Force's effort to maintain air dominance. A key objective is to reduce the aircraft's radar cross-section. This is achieved through advanced design techniques, including smooth, angular surfaces that deflect radar waves away from the source, rather than reflecting them back to enemy systems. Notably, the removal of vertical stabilizers, a feature seen in some concept designs, plays a critical role in reducing radar reflections from typical aircraft surfaces. Additionally, NGAD is expected to incorporate advanced radar absorbent materials, which scatter or absorb incoming radar waves, making it harder for radar systems to detect the aircraft. Regarding infrared signatures, engine heat is a key detection risk. The platform will likely feature advanced cooling systems to reduce the heat emissions from its engines and exhaust, thus lowering its thermal signature. This not only helps avoid detection by IR sensors, but also improves engine efficiency and longevity. NGAD will also address acoustic stealth, reducing the noise generated by the aircraft's engines. While details are still evolving, the aircraft will incorporate technologies to minimize its acoustic footprint, helping it operate more quietly in hostile environments. A hallmark of the program is the transformation of sensor technologies and how they're integrated into the aircraft's systems. NGAD fighters will feature streamlined cockpits designed for stealth and aerodynamics, reducing the physical space for traditional pilot visibility. To compensate for this, the program integrates advanced electro-optical sensors that provide a 360-degree real-time view, greatly enhancing the pilot's situational awareness. These sensors don't just improve visibility, they merge visual data with targeting information, allowing pilots to engage threats from any angle. In line with modern combat strategies, over-the-horizon capabilities are emphasized. The sensor suite will enable pilots to detect, track, and engage targets from much greater distances, minimizing the need for high-speed engagements and instead focusing on long-range combat. This reflects a broader shift in aerial warfare, where sensor superiority trumps speed and agility. At the heart of the sensory capabilities is Active Electronically Scanned Array, AESA radar. These radars are far more advanced than earlier models, featuring no mechanical moving parts and offering superior durability and reliability. AESA systems can scan and track multiple targets simultaneously across vast volumes of airspace, while also managing tasks such as electronic warfare and surveillance across the electromagnetic spectrum. Another key focus is the advanced weaponry that these future fighters might wield. One of the areas of exploration is the use of directed energy weapons, or DEWs, such as lasers and microwave systems. These technologies offer substantial benefits, particularly in terms of cost-effectiveness and precision. Unlike traditional munitions, which can cost millions per missile, DEWs fire for only a few dollars per shot, making them economically attractive for continuous defense operations. The Air Force's SHIELD program, Self-Protect High-Energy Laser Demonstrator, is an ongoing initiative focused on developing laser systems that can defend aircraft by disabling incoming missiles. This is seen as a promising defensive capability for NGAD, where DEWs could provide real-time protection against threats. However, while the potential is significant, these technologies are still in the experimental phase. Challenges such as managing the heat generated by these weapons are critical, as the excess heat could compromise the stealth capabilities of the aircraft if not managed effectively. Moreover, atmospheric conditions can affect the power and range of these energy weapons, limiting their use over long distances. As a result, the primary envisioned role of DEWs is defensive, focusing on missile interception rather than directly engaging enemy aircraft or ground targets. In addition to DEWs, the NGAD program is also focusing on long-range missile integration. Modern air combat strategies are increasingly shifting toward beyond visual range engagements, allowing aircraft to strike from a safe distance without entering enemy airspace. Furthermore, the incorporation of hypersonic weapons is under consideration. These weapons, capable of traveling faster than 5 times the speed of sound, are designed to penetrate modern air defenses by virtue of their sheer speed and maneuverability. These weapons not only shorten the response time for both offensive and defensive operations, but also increase the difficulty for enemies to intercept them. Central to the NGAD program are 2 key concepts: the Penetrating Counter-Air, or PCA platform, and the Collaborative Combat Aircraft, or CCA, both designed to overcome the limitations of current stealth fighter technology and revolutionize air combat. The PCA platform is being developed to extend the operational range and payload capacity of stealth fighters, addressing gaps in current air power, particularly in regions like the Pacific. where long distances between bases and targets present significant challenges. The PCA fighter is expected to be a next-generation aircraft capable of long-range strikes without sacrificing stealth. Complementing the PCA are the collaborative combat aircraft, unmanned drones that will serve as AI-powered wingmen. These drones are designed to handle high-risk missions, enhance situational awareness, and carry additional weapons and sensors. Working alongside manned fighters, they will significantly boost combat effectiveness while reducing risks to human pilots. Both the PCA and CCAs will be fully integrated into a network-centric combat system, allowing for seamless communication and data sharing across platforms. This integration, powered by AI and cloud-based systems, will enable real-time decision-making and transform fighters into command nodes in a multi-domain operational environment. As mentioned at the beginning, the program, once expected to progress smoothly toward developing the world's first sixth-generation fighter, has encountered a significant pause in 2024. The U.S. Air Force made the decision to pause the program as it reassesses the design and overall direction of NGAD. This pause stems from the need to address several key concerns, including rapidly changing global threats, escalating development costs, and the challenge of balancing capabilities with affordability. One of the primary reasons for the pause is the evolving global security landscape. Since the NGAD concept was first introduced, the threat environment has shifted considerably. To ensure the program's relevance against future adversaries, the Air Force is rethinking how the NGAD platform can meet emerging technological and strategic challenges. This reassessment considers the rise of hypersonic weapons, advanced electronic warfare systems, and growing competition from near-peer adversaries such as China and Russia. These developments have prompted the Air Force to reconsider NGAD's design to ensure it remains effective over the long term. Another critical factor driving the pause is the cost-effectiveness of the program. With the estimated cost of each NGAD fighter reaching as much as $300 million per unit, 3 times the cost of an F-35, the program's financial viability is a growing concern. For comparison, the F-35 typically costs between $80 and $100 million per unit. The steep price threatens to limit the number of aircraft that can be produced, which raises concerns about fleet size and overall affordability, particularly within the constrained budget of the Department of Defense. This issue is further compounded by delays and rising costs across other critical U.S. Air Force programs. The F-35 Joint Strike Fighter program, for instance, continues to experience setbacks, especially with its Block 4 modernization effort, which has seen costs rise to $16.5 billion. Additionally, planned F-35 purchases have been reduced due to budgetary constraints, with procurement numbers dropping from 48 aircraft in 2024 to 42 in 2025. Similarly, the development of the B-21 Raider, which is set to replace the aging B-2 Spirit and B-1 Lancer, has encountered cost overruns. Although the first test flight has been completed, unit costs could range between $300 and $750 million, with further challenges remaining in terms of controlling long-term costs and adhering to the development schedule. The Sentinel ICBM program, which aims to replace the aging Minuteman III intercontinental ballistic missiles, is also experiencing budgetary challenges. Initially estimated at $100 billion, the program's costs have ballooned due to supply chain issues, workforce shortages, and the complexity of constructing new command and control infrastructure. Amid these mounting costs and delays, the U.S. Air Force has also begun to explore the possibility of reviving a light fighter concept as an alternative or supplement to the costly NGAD program. The light fighter concept aims to strike a balance between high-end capabilities and cost-effectiveness. It leverages open systems architecture, digital engineering, and modular design to allow for easier upgrades and lower maintenance costs, making it a more flexible solution in a rapidly evolving threat environment. Moreover, this concept aligns with the USAF's evolving strategy of deploying collaborative combat aircraft. The light fighter would handle lower-intensity missions and provide air superiority in more predictable scenarios, allowing more advanced platforms like NGAD and F-35 to focus on complex, high-threat environments. While still speculative, the light fighter concept could mark a shift toward a high-low mix of aircraft, similar to the strategy used in previous decades with the F-16 and F-15. So, while NGAD represents the future of air dominance, its high price tag and evolving requirements raise questions about its sustainability. Whether through NGAD, a potential light fighter alternative, or a combination of both, the path forward will require careful balance between maintaining technological superiority and ensuring affordability in an increasingly complex and constrained defense environment. In the end, NGAD remains a symbol of cutting-edge military innovation, but whether it will be the definitive answer to future threats or part of a broader, more adaptable solution remains to be seen.